this is the network that we started with. We're now going to solve it using superposition. Superposition is a property of linear networks. In fact, it can be used as the definition of a linear network. In network theory, where we have R, L's, and C's, the terminal relationships are linear differential equations. And so when you combine any number of these, you end up with a linear differential equation. And superposition holds because the network is linear. And what we mean by that is, suppose I want to solve for the output voltage. Well, we have some function, say of A, V1. We have two sources, B, V2, and these are the amplitudes of the sources. Well, the definition of superposition and linearity is that this is F on V1 plus B F on V2. That says, what this tells us is that the solution to the network when we activate both sources simultaneously is the same as if we just activated the sources one at a time. That is, I could set V2 equal to 0, that drops out, and I can solve for the network with just V1 activated. Then I can, so this would be V out 1. Then I can activate V2 and kill V1, set V1 equal to 0, solve for the network, and then I get the contribution to the output due to source 2. And then to get the total output, I just add the individual contributions as I activated the sources one at a time. Now, remember that for a network always has this sort of form. We have a numerator polynomial or coefficient divided by the system function times the independent source V1 activating the network, plus I have a numerator polynomial n2 divided by the system function times V2, and so on. Any number of independent sources that drive the network will always end up with this sort of a expression. So this tells me that in order to get the output due to all sources activated simultaneously, like when I solve the network to begin with, we'll end up with this expression. But I can also just activate the sources one at a time, get the contribution of the output to each of the individual sources acting alone, and then add the contribution of each source acting alone to get the output when all sources are activated. So, in order to do this, what we need to do, this tells us then we have to solve, if we have n sources, or in this case 3 sources, we have to solve 3 different networks when we're using superposition. So what we need to do now for this network is look at the equivalent circuit when we activate the sources simultaneously or individually. Now, since we have all voltage sources here, these are our independent sources, V1, V2, Vd. To kill a source or set it equal to 0, we replace a voltage source with its internal impedance. An ideal voltage source internal impedance is 0. So we replace voltage sources with a short, and if we have current sources, we replace them with an open. So here we're going to activate V1 with V2 equals 0 and V3 equal to 0. Well, when V2 is 0, or Vd, V2 and Vd are 0, we replace these with a short. So let's draw our equivalent circuit. This is V1 plus terminal, the non-inverting terminal of the op-amp. This is our V1 or a Vin. This is the inverting terminal. We have R1. Now we replace V2 with a short, so we end up with R2 to ground. We have our RF. Now we have R out and the voltage source AV in. This is our operational amplifier. And then we replace VD with its internal impedance, which is a short. We're turning this one off. And then we have V out over RL. So this is the equivalent network for activating V1. And then we solve, we'll call this V out 1. We solve for V out 1 on that network. Then the second network is we activate V2, and we set V1 equal to 0 and VD equal to 0. Now let's look at that equivalent network. Well, if V1 is set to 0, this becomes a short. So we have R in, the positive terminal is down at ground now. We're replacing this with a short. This is the minus terminal. Here's our V in. And then we come, this is ground also. Now we have R1. And we're activating V2. So we have R2 and V2. We go to the feedback resistor. Then we replace VD with a short. We have our operational amplifier driving. Whoops. So this is AV in. This is R out. Now we have RD to ground. And then we have our output with RL. So that's the network we solve to get V out 2, the contribution to source 2 to the output. Then I'll do it up here. We're going to activate VD and set V1 and V2 equal to 0. So if we do that, we replace V1 with a short. So this goes to ground. V2 is replaced with a short. And we have VD activated. So this is V out due to D. So these are the three networks that need to be solved in order to use superposition to get the total output when each source is activated. So I'm going to do one of these and then give you the equations for the other networks, and you can do all the algebra. So let's look. What we're going to end up with here first is, once I get each of these contributions, what's going to happen is my output voltage is going to have this form. We're going to have V out 1 plus V out 2 plus V out 3. And this will be some N1 over the system function times V1 plus N2 over the system function V2 plus ND over the system function times VD. This is what we're looking for. Okay, now I'm going to redraw. We'll activate V1. We'll use this network here, and I'm just going to go ahead and write that up here so I have some board space. So we have V1, our plus terminal, our minus terminal of the op-amp. We have R1 to ground. We have R2 to ground. We have RF, our feedback resistor, then our operational amplifier, and then we just replace source VD with a short, and we're looking for V out due to source 1. So we have set V2 and VD to 0. So now we'll solve the network for VO1. As before, we need to look at the input and the output using node voltages. This is VO1. The node voltage here is V1 minus Vn, going from this terminal to ground. We have minus Vn plus V1. Now I'm going to define some terms here to make it easier in solving. We have R1 and R2 in parallel. So I'm going to call this RA. And we have RD and RL in parallel, and I'm going to call that RB. So RA, 1 over RA is 1 over R1 plus 1 over R2. 1 over RB is 1 over RD plus 1 over RL. We'll use that, and it'll simplify things. So I'm going to go ahead and write that right now. Those are our definitions. It'll just make the algebra a lot easier. So this is RA, and this is RB. So let's write our equations. At the input node, currents leaving is positive. So the current through Rn is minus Vn over Rn plus V1. The current going through Rn is the voltage across it divided by Rn. So in this case, it's minus Vn over Rn. Okay. The current leaving through this resistor is the voltage at this node with respect to ground. Well, the voltage here is minus Vn plus V1, or I'll write it as V1 minus Vn over Ra. And then the current leaving through RF is the voltage here minus the voltage there. Voltage here is V1 minus Vn, and we subtract the output voltage V out 1 and divide by RF. And that's equal to 0. Now, I'm going to multiply through by RF. Or first we'll group our terms. I'm going to write minus Vn. We have 1 over Rn plus 1 over Ra plus 1 over Rf. These are our Vn terms. And then we have plus V1 over Ra. That's that term. Plus this term. So it's 1 over Ra plus 1 over Rf. And then minus VO1 over Rf. And that's equal to 0. Multiply through by Rf. And we have minus Vn times 1 plus Rf over Rn plus Rf over Ra plus V1, 1 plus Rf over Ra minus VO1. Now, since Ra, 1 over Ra is 1 over R1 plus 1 over R2, then Rf divided by Ra is Rf times 1 over R1 plus 1 over R2. And remember from before, we defined this to be G, our inverting gain. So I can replace this in the following manner. I'm going to move this over to the right hand side. So I have V1 times 1 plus, well, RF over RA is G, so it's 1 plus G minus VO1 is equal to Vn times 1 plus RF over RA is G plus RF over Rn. And then we solve for Vn. So Vn is equal to V1 times 1 plus G minus VO1 divided by 1 plus G plus RF over Rn. Okay, so that's our input equation. We have Vn. Now we look at the output equation. So at the output node, we're going to take currents as leaving as positive. So current going through RF is VO1 minus V1 minus Vn over RF. Current going through R0 is VO1 minus AVN over R0, and the current going through RB is VO1 over RB, and that's equal to 0. Combining like terms, we have VO1 times 1 over RF plus 1 over R0 plus 1 over RB. That's that one, and that one. And then we have a minus V1 over RF for there. And then our Vn's, we have a minus minus, so a plus Vn times 1 over RF minus A over R0, and that's equal to 0. Multiply through by RF, we have VO1 is 1 plus RF over R0 plus RF over RB minus V1 plus Vn times 1 minus RF A over R0, and that's equal to 0. Now we take our Vn from here and substitute it in there. Before I do that, I'm going to first multiply through by R0 divided by ARF. So I'm going to write this as VO1 times R0 over ARF. So we have 1 plus RF over R0 plus RF over RB minus V1 R0 over ARF plus Vn times R0 over ARF minus 1 is equal to 0. Now we put in for our Vn into this equation. So as before, what we do is we'll put this in and then we multiply through by the denominator of Vn. So I'll write the equation here. So this will now become VO1 R0 over ARF times 1 plus RF over R0 plus RF over RB minus V1 R0 over ARF plus our Vn which is V1, 1 plus G, minus VO1 over 1 plus G, plus RF over Rn, and that quantity is times RO over ARF minus 1. That's equal to 0. Now, I'll let you do the algebra, and I'll give you the result here. Alright, I've written the equation up here. We're going to simplify this a little more. We need to work on the left-hand side. If you work on this left-hand side, you should get this expression here. We're keeping the right-hand side the same. All I've done is written it so that I'm gathering the R zeros together. So that's what we've got here, and this is the final form. Is that here again we have the denominator polynomial, or what we call the system function. That's our D. I've written this here. That's our D value. So this is D, which I've written here. And here are the definitions of RB and RG. RB is the parallel combination of RD and RL, and G is RF divided by the parallel combination of R1 and R2. So we have V1 times this divided by D. So as you can see, that this is the V1 portion of the output voltage that I got before when I solved the network in its entirety earlier. So this is the contribution to the output voltage of the output voltage due to V1 being activated. Now we do the same thing for the other two sources, and I'm not going to go through it like this, but I'll give you the equations to work with. We'll work through those, and then you can do all the algebraic manipulations to get the final value. Now, we're going to activate V2 and set all the other sources to 0. So we've replaced V1 and VD by short circuit to kill those sources, and now we solve for the output, VO2, in terms of V2. Okay. Again, at the input, we sum currents as leaving as positive, so the voltage across Rn is a minus Vn over Rn, and we have a minus Vn over R1, and then we have a minus Vn minus V2 across R2, and a minus Vn minus a, or minus VO2 that the current across RF is this voltage minus this voltage divided by RF. This is minus Vn, and then minus VO2 divided by RF, and that's equal to 0. I'm going to, since we have all minus signs, I'm just going to multiply through by minus. Group-like terms, so we have Vn is 1 over Rn plus 1 over R1 plus 1 over R2 plus 1 over RF. That combines those terms, and then we add V2 over R2 and plus VO2 over RF. That's equals 0. Okay, so that's one equation. Now the output equation is summing the currents as leaving as positive. We have VO2 minus a minus Vn over RF plus VO2 minus AVN over RO plus VO2 over RL is equal to 0. Again, combining like terms, we have VO2, it's 1 over RF, that's that term, plus 1 over R0, that gives us that term, plus 1 over RL. And then a minus minus gives us a plus VN, times 1 over RF, minus A over R0, and that's equal to 0. So that's our other equation. So with this equation and this equation, you can solve for Vn in this equation, put it in this equation, and solve for VO2, and you'll get the contribution of VO2, or the contribution of V2 to VO2, which will be the component, this component here, like when I solved the network before. Now, the last one is we activate VD and kill V2. So we kill V2, replace it with a short, and if we activate VD, we have RD, VD, and RL. So again, we write the input equation. We have minus Vn over Rn minus Vn over, we'll replace this with Ra. So it's minus Vn over Ra. That's a parallel combination. And then we have minus Vn minus VOD. That's our output voltage due to source VD. And that's over RF. And that's equal to 0. Again, we'll multiply through by minus sign, combine like terms, so I end up with Vn, which is 1 over Rn, plus 1 over Ra, plus 1 over Rf. That's those terms, plus VOD over RF is equal to 0. So that's the input equation. At the output, summing currents leaving is positive. We have VOD minus a minus Vn or plus Vn over RF plus the current through R0, which is VOD minus AVN over R0. Current through RD is VOD minus VD over RD plus VOD over RL is equal to 0. Combining like terms, we have VOD 1 over RF plus 1 over R0 plus 1 over RD plus 1 over RL. That's those three terms. And then we add the Vn, 1 over RF minus A over R0. That's that term and that term. And then minus VD over RD is equal to 0. So that's the other equation. So, if you solve for Vn in this equation, put it in this equation, crank it out, you'll get the contribution of VD to the output. So then you add the three outputs, VO1, VO2, VOD, like this, and that'll get you the same answer as I got when I solved the network at the beginning of the video. So that's how you use superposition. You just activate the sources one at a time, solve the network for the output due to that source being activated, then do the next source, activate it, kill all the other sources, find the output due to that source that was activated, and so on. Then when you're done, you add all the outputs, and then that gives you the answer. So that's how you use superposition. Whenever I have fairly complicated networks like this, I check myself by performing a flow graph analysis. This is the flow graph for this network. I'm not going to get into how I created this. That's for a future lecture. But let's just say we have our three independent sources, V1, V2, and VD. And here's our output node. I define the YPA and YPO to be these values. YPA is the sum of the admittances that touch node VA, and YPO is the sum of the admittances that touch the output node. Then by Mason's gain formula, 1 minus the sum of the loop gains defines our denominator, our system function. So there are two independent loop gains. There's one here and there's one here. So we have 1 minus, we have first this loop gain, which is RF-YPA times RF-YPO, and then we subtract this loop gain. Well, the loop gain is negative, so subtracting the negative adds. So starting here, we have A R0YP0 times RF-YPA. So that's that loop gain. Then if you multiply by this quantity, R0YP0 RF-YPA over A times 1 minus the sum of the loop gains, you get the denominator, system function. This is our system function. And it's equal to this quantity once you perform these operations. Now, to get the numerator gains for each of the individual sources, we look at the forward paths from that source to the output. So for example, for path 1, for voltage source 1, there are 3 paths. We have this path going in the forward direction, we have this path, and we have this path. So there are 3 paths to add, and that will give us our gain, our G1. And then you multiply it by this same factor, and if you perform those operations, you'll get this value for our numerator polynomial. Then, for source 2, its forward gain, there are 2 paths there. There's this path, so 1 over R2 YPA times 1 over RF YPO, and then it's 1 over R2 YPA times minus 1 times A over RO YPO. And then if you perform those operations, you'll get this value here. And the same thing for source VD. There's only one forward path, and that's 1 over RD YPO. And if you perform that, you'll get that. Then, once we have those 3 contributions, we just go ahead and sum everything to get the output. The output voltage will then be N1 times V1 over D, the system function, plus N2 V2 over the system function, plus ND over VD divided by the system function. And we'll get the same value as we did before. So this is a good check if you want to check yourself, and this gives you a shorthand method to getting to the solution. So that wraps it up for superposition on this one. In order to solve these networks, you have to be very proficient at algebra. It's easy to make mistakes. And it's always good to check yourself when you have complicated expressions. To aid, I usually group things and then give it a special symbol, like I did with capital delta. Multiply things through and then go back and make the substitutions. You're less likely to make mistakes when you make intermediary definitions and substitutions.